my name is Shaofen, and today I'm going to introduce our work, Dynamic Routing Network, which is a dynamic architecture for higher inference efficiency. And this is a joint work with Shuyao and Wang Wei from NUS. Deep neural networks have revolutionized many domains by designing increasingly larger and more sophisticated architectures. While making deep models more accurate typically comes at the cost of increased computation and memory resources. However, in real-world applications, most inputs actually do not need an expensive model to be correctly classified. So, one key observation here is that inference with a static architecture that processes all inputs, while the same transformation would incur unnecessary computational cost. One can imagine that a well-designed dynamic model can achieve accuracy comparable to a large model, while in the meantime, with much higher efficiency as a dynamically pruned small model, by skipping unnecessary computation. So, at a high level, the main idea is to skip unimportant model components depending on the current input. And dynamic inference architectures can be achieved at several structural levels. For example, the activation of the channel level, and the right panel shows a dynamic channel pruning network. And there are also many works proposing to dynamically skip layers, modules, or submodels to save computation by selectively computing only a subset of model components. Formally, the dynamic architecture customization can be regarded as a multi-step decision process. Specifically, for each layer in order, an auxiliary hypernetwork will take the layer input and then dynamically select the proper subset of model components for producing the layer output. In this paper, our key idea is to produce the prediction at the branch level, which is more fine-grained than the layer, module, or submodel level, and thus can achieve better customization for higher efficiency. And meanwhile, since the number of branches for selection is relatively small, so the prediction with the hypernetwork for the right branches is easier and thus more accurate than the activation or channel level. Another novelty of our DRNet is that the backbone network, that is, the base architecture for selection, is built upon state-of-the-art NAS architectures. Specifically, the backbone network is a stack of cells, and each cell contains a series of interconnected transformation nodes. While instead of searching for the connection topology and the corresponding transformation for each node connection as in NAS, each node here is simply connected to a subset of preceding nodes. So this is the backbone network of our DRNet. Now let's take a closer look at the connections between transformation nodes. The crux here is to introduce B plus 1 transformation branches instead of only one branch for each node connection. These B branches can be homogeneous or heterogeneous, which are trained to specialize in different inputs. And there is also another fast-forward branch adopted, for example, identity mapping, so that we can efficiently forward the current input without heavy computation. Then, at runtime, the hypernetwork routernet will take the current input and dynamically assign importance weights to each branch, so that we can selectively bypass unnecessary branches for much higher efficiency. Importantly, we recalibrate the importance weights with Gumbel softmax and reparameterization, so that the whole network can be optimized end-to-end effectively. We evaluate DRNet on diverse datasets and compare it with extensive baseline models. We summarize the main results on the left table, which shows that DRNet can achieve comparable accuracy with several times less parameter size and flops. And the right-hand side is the branch selection ratio of a representative cell, which shows that different inputs indeed require diverse transformation. And DRNet successfully route inputs to different branches at runtime. For more detailed formulation, discussions, and experimental results, please refer to our paper. Thank you.